Alrighty, guys, you ready for the last bit? Any comments before we get started on the last part? Okay, then so again, you can find links on the syllabus to these teaching notes that I've been using for the lectures. You can find them on the syllabus, and you can find the syllabus, of course, on Canvas. So this here is our PDE. T is running. T is positive. Like we have the initial condition. T is positive, and X here is going to be in R. Okay, so we're going to grid up. We're going to grid up this rectangle, and so we're going to make a. What will it be? We'll have. See if I can make a picture here. So this is X down here. X is in R, so it's running on the real axis. I'll have an upper bound. This is what I'll call XH, high and low. And up here we will have time. So this here's time is equal to 0. And then we'll move up. We're interested in presumably something that happens at, say, time capital T. So what we will have is we have prescribed the behavior. We've been given the behavior of U when T is equal to 0. Okay, so we have been prescribed the behavior on this boundary. So this is our, so we are given, U's values for, so we're given U's values for T equal to 0 and X in R. Right, so this is going to give me U 0 X. Those are those values. Those are those values. Then we've been given the values for U when X is big. Okay, so we've also been given this. We've been given this for T positive when X is big. So here, I mean, big should ideally be all the way up to plus infinity, but of course, our computer, we have to have a cutoff somewhere. So we've been given this function. This is TXH. So let me use a different pen color here. Those are those values we have here. And then finally, we've also been given the values of U when T is positive and X is small. Small, this is when X is at the lower threshold, XL. This is U, T, XL. Let's see if I have another pen. Running out of pen colors. I'll use the blue one again. So this is what we have over there. So this U shape here, this is called the parabolic. This is called these T's and X's are called, and the word you want to look for is the parabolic boundary. Okay, so you've been prescribed use values, the solution, you can describe those on the upper and the lower. So think about it. Think about it for the if you think about it for the if you think about it for the put option, right, then you would have g of x would be k minus x, positive part, right? So then, so that means that you have your u at time 0 is equal to k minus x, positive part. And I shouldn't call it u, but it's, let me call it something else here, right? So this is on that parabolic behavior, on that parabolic boundary, and then you would have, what is the value of f when the stock price is 0? What is the value here? Well, this would be when x is equal to 0. You have 0, and then when x is very large, what would be the boundary here? Well, when x is very large, you're going to get this shouldn't be k, this should be k. So you're going to get a 0 here. Right. So for the Black-Scholes world, right? So here we have ft is equal to 1/2 x squared sigma squared fxx, and f of 0. This was that k minus x positive part, right? So if you were to discretize, and this is exactly what you'll be doing in the homework. So you have your lower point, probably going to be 0, right? And then you'll have your upper point. I don't know what you're going to put here, 5, 10, 5 or 10. So here you put, what is the value of the put option when the stock in Black-Scholes is equal to 0? Well, here you put k. So that would be the value you would have. That would be the value you would have here, right? And then so for very large values, you would have to prescribe what is the value of the put. But if it's very large, you're probably going to get a 0. And then what you do in between, well, we start out here by being red, and that's this guy here. You have x out of the horizontal axis, and then you'll have time. You'll have time of the vertical axis. So that's how you do it with a put option. But you can see that there's trouble. There's trouble with call options. Why is there trouble with call options? Well, then your g of x would then be x minus k. And so your initial point would be the same again. F at 0x, this would be exactly x minus k. And so what would be the value here on the left part of the parabolic boundary? It'll be when the stock is equal to 0. Okay, so then you'll have 0 minus k, so that's going to be a 0. But you see, the problem happens here. The problem happens when you go to something large here. What would you put up at plus infinity? What would you put here? Any guesses? Like what we did for the put was we said, well, what would happen is that when you're very large, so x here is going to plus infinity, you're going to get past k, you're going to get the positive part of something negative. That's going to give me the 0. But what happens down here when x is going to plus infinity? What is x minus k going to go to? Yeah, I mean, that's going to go to infinity. So how are we going to get this? This is not going to work. But we can't. This cannot be. This cannot go into a computer. Cannot go into your C++ code. We can't prescribe the value plus infinity out here. So what to do? So what do we do? Any ideas on what we could do to overcome it? How would you price a call option? One suggestion could be what? Well, we could price the put and use, what could we use? Very good, Amy. This is exactly what we can do, and use put call parity. I'm sure everybody has seen put call parity before, but it's not complicated, right? The way that we do put call parity is you play around with these pictures. So this is the put, and you have the call, right? So how do we get from this to that? Well, I also have the stock. So the stock, right, that's the one that looks like this. So what would I need to do? I need to shift this up with what? I would start out here. How do we get this thing to work? I would add, subtract. So if I take x, I need to move this thing down a little bit. So x minus. So the key with these pictures is you always start out from the right. Right. So this is what I want to get. You start out from the right. So we see the slope out here. I need to generate the slope somehow all the way out to the right. Okay, so I need to lower the stock down. I need to lower it down so I have the right behavior out here. That was a k, right? So I need to go down to minus k. So I take the stock minus a k. That's going to give me this picture. And then what? Then this part out here on the right is good. But I have a problem in here. So what I need to do is I need to add a put. Because if I take a put here and I add it together with this one, I'm going to get a flat line here. So I need this thing plus, and then it'll be the put is k minus x. If I do that, I should get the call, which is x minus k plus. So this is the put call parity. Here we have the call. Here we have the put. Here we have the stock. And here we have the bank. Right, so this is one way to replicate the call, trading in the stock, the bank, and the put. Very good, Amy. So this is one way to do it. The other way to do it, you can see I wrote one here. There is another way to do it too. Right. So instead of a DA Clay, so can I spell DA Clay? I don't even know if I can spell DA Clay. Okay, direct, I think it's something like this. Instead of a DA Clay boundary condition, at the right endpoint. you can use a Neumann. Neumann, is it 1 or 2? Neumann boundary condition. So what that says is that when you're out here, when you're out here on the right, instead of prescribing that behavior, what you prescribe is a derivative. So fx instead of prescribing the value, you prescribe the value of the derivative. So fxt at infinity and any guesses on what this one here should be? Amy, you said the one without the x should be plus infinity, but now what should it be when I take the derivative? So if you want to keep it here, so I put xh here. What should we put here for the derivative out at plus infinity? What should the derivative be out here, this upper boundary? For the call option. Any guesses on what that could be? How does the value in the call change when the underlying stock price changes for very, very large values of the underlying stock price? Say that the underlying is like 1 million, and we're thinking about how does the change in the call price, how does it change when you go from 1 million to 1 million plus 1? Not quite, Alice. How does the call price look like when you're all the way out here on the right? Well, it looks a lot like this line here. And if you compute the derivative of this line here, you're going to get a you're not going to get a 0, you're going to get a you're going to get a 1. Right, and this here is because the derivative of x minus k for x large, this is equal to 1. So you could, instead of using these here called Dirichlet, these two here called Dirichlet. I can never spell Dirichlet. These are called Dirichlet conditions. You could replace, or you don't have to worry about the one that's fine. It's the one with the plus infinity that's troublesome because you can't get it into a computer. You could put a derivative here and maybe you could get away with that. So there are two proposals. Of course, I like Amy's a lot because you just use put call parity. Like focus on puts and use put call parity. This will give you the price of the call simply by using this little replication argument that I'm sure you guys have played with before, right? You can relate put, call, stock, and bond prices using a simple formula. Okay, so this was just to tell you that in specific cases, you can specific cases like the ones that we're interested in for put and call, you can prescribe what this behavior is on the boundary. Okay, so so we are now looking at the heat equation. We don't have a stock here. The underlying can be thought of as Brownian motion. We have this behavior, we have prescribed the behavior, and here we're using Dirichlet conditions, like these two here, dr again Dirichlet. We could have had Neumann, there could have been Neumann conditions here. You could have had a UX, and you could have had a UX here. We don't have that for the analysis that I'm about to present here. Okay, so so we're given that, and now we grid out. We're going to make a grid. We're going to grid out. We're going to grid out. So time runs between 0 and infinity. This is where my t variable belongs. And then my x variable, this is the one that runs between xl and xh. This is where my x variable belongs. So we're going to grid out this rectangle. And how we're going to grid it? Well, we look at delta t. Maybe I'll run this here up to just capital T to make it more specific. I'm just interested in up to capital T. We'll grid out delta t will be say t divided by m. Right, so we have my value is tm would be 0, and then it'll be delta t, 2 delta t, all the way up to will be m delta t, which of course is equal to t. Right, so here I'll have count them. You'll have m plus 1 time points. So that'll be tm. We'll also have a x variable. That's the one that lives over here. The convention that I'm going to be using is I'll take the difference, so xh minus xl, and then I'll divide here by n plus 1. This is just a convention. I divide by n plus 1. And then my time points, those will be xn, right? You'll belong to xl. That's the lower point. Then it will be xl plus delta x, and then all the way up to xh. So here we will have n plus 2 time points. No, not time points, space points. So that's my grid. I'm interested in say an option that expires at time capital T. Maybe that's half a year or 1 year. I'll grid out the underlying variable here. It'll be round in motion. Could be as in the other pictures, it'll be geometric round in motion. Then it'll be positive. So put in a bunch of points here, put in a bunch of points here, and have a big rectangle full of points. Right, and so the idea would be to approximate my u n m. This thing here, just like fn before, this here is going to approximate. This is going to approximate the solution evaluated at tm and xn, right? And these time points are given up here. Tm is something that runs in the time grid. Xn is something that runs in the spatial grid. And so m is upstairs. This is going to be the time variable. This one here, this is time. This one here. This one here, this is going to be the spatial variable. these here are going to call spatial points. Right, so before when we had f, we would just have fn, and fn would approximate f evaluated at tn, and now it's going to be different. We're going to have two, because we have a two-dimensional object. We have time and the spatial variable. Okay, so we go back to the PDE. We were seeking to replace. So we have the u function over here satisfies ut is equal to uxx. Right, so what we're going to do is we're going to replace this here with the second order difference operator. That was the one we had from way back in the day, maybe last time, the time before. That was the one that said that if you take d squared applied to a function, I'm not calling u, let me call it, we had the functions that were f before, f evaluated at point x, this would be f of x plus h minus 2u x plus, we should call it f here, plus f of x minus h divided by 2h. So that was the second order difference operator. The ut, well, this one here, this is a time derivative. So here we can use Euler's methods, and this trapezoidal this is not how we spell trapezoidal, trapezoidal method. So here we will have flexibility depending on which method we're using, but the uxx is always going to be this second order difference operator. So let me try to write that out. So the second order difference operator applied to that u, what will it look like? So we will have u, so uxx evaluated at tm and xn. This is going to get approximated by this difference operator over here. This is going to get approximated by, so what we need, m is fixed, right? We're taking derivative with respect to the second variable. So m is fixed. So we'll put an m up here. M does not vary, right? What varies is the x variable. And so what happens there is you go one out. Okay, so we go one out, that'll be an n plus one. And then we subtract away 2 times where we at. That will be u m n. Okay. And so here we also have 2f. So we add, then we have minus 2, and then we add f. That'll be my u. There's no variability in the time variables. So put an m up there. And then you go one back. So this would be n minus 1. And then you divide by 2 of the time step. So h here, this would be 2 delta x. So that would be how we deal with this one all the time. And now here we have a choice to make. Which one we want to make depends on which method we're using. And if we use the explicit Euler, so we use the explicit Euler. So we'll have I have the explicit Euler. Then what we'll have is ut, this will be u, and then the time derivative will be m plus 1 minus um divided by delta t. Right, so I want to match that up with what I have over here. Like explicit Euler means I'm using m's here. If I were to use the implicit Euler, I'll have to use m plus 1. So let me plug that in. This will be u m n plus 1 minus 2u n m plus u n minus 1 m divided by 2 delta x. Feel like I'm messing something up here. This 2 there is not the right one. It should be up here. It should be a square. Is that right? Yeah, I put the 2 in the wrong place. This one here should be a square. So delta x squared. That looks better. And so we see again that this has an explicit structure to it. This delta t can go on the other side. I'll get that the way to deal with a numerical approximation of the explicit of this heat equation up here, I'll get that this is un m plus 1. This is equal to the previous one plus, then you multiply delta over delta t divided by delta x squared times this difference u n plus 1 m minus 2 u n m plus u n minus 1 m. That's the explicit Euler. And this ratio here is delta t over delta x squared. This is just often called alpha. And then I can combine because I have a term here and the same term is in here. I'll end up with 1 minus 2 alpha u n m plus, and then I'll have what do I have? I'll have alpha u n plus 1 m plus alpha u n minus 1 m. And this is going to be true for all the points for n equals 1 all the way up to n. This is the explicit scheme. And so on the picture, what is happening is if we reproduce this picture we have up here, but I'm looking at it now on the grid. If I'm gridding it out, the way that it looks like is I have my XL over here, I have my XH over here. And so what we're pretending is we're coming up to time m. So there's some time point up here. This is this here is my Tm. And so there'll be a discrete grid. Right, and I know the values here. So when I do the Euler scheme step, I will know these ones here, the unknown, and the other one I know is up at the next one. I'll also know this point here, and I'll know this point here. Right, so I'm not saying anything about n equal to 0, and so this is just a note here. If I have n equal to 0 and n equal to n plus 1, they are given values, right? So these points here, right, these dots here, the unknown, and the ones on the side, the unknown. But of course, what is not known are all these values in here. These ones here, these ones, they are to be determined. And what the explicit order scheme allows you to do is it does allow you to determine these. And what you need is, if I want to pick one of them, if I want to get that guy, so whatever number it is, this is number n. What I need to know is you need to take what you have or before at three different places. So if I want to get this guy, what I need to draw on is this guy has to go up there, this guy has to go up there, and then this guy has to go up there. So it's explicit because you just take 3 points that you already know, and you feed them into the formula, and it gives you this one. So that was the explicit one. If you look at the implicit one, this is when the picture, then this here becomes more complicated. If you look at the implicit one, the formula changes. So if you look at the implicit order, we're still going to have that derivative, but now on the right-hand side where we evaluate, it's going to be different. I'll have to put n plus 1 everywhere. So let me try to do that. I'll have un n plus 1 minus un n plus 1 divided by delta t. It's going to be exactly what you had before, but now it's going to be n plus 1 up here. Minus 2un n plus 1 minus plus un minus 1 n plus 1 divided by delta x squared. And then we simplify, we move the stuff to the right-hand side, we will get u n m plus 1 is equal to u n m. So that's the same as before. We move delta over. So we're going to get delta t over delta x squared. And then all this stuff inside a set of parentheses. So that was 1 minus 2un n plus 1 plus un minus 1. And again, as before, this here is my alpha. But you see now it's more complicated because I have n plus 1 here and I have n plus 1s everywhere over here. So I can combine, I can move stuff to the left-hand side. I will then have, I will have 1 plus 2 alpha times un n plus 1. So I'll move this term to the other side. I'll also move the other terms. Minus alpha un plus 1 n plus 1 minus alpha un minus 1 n plus 1. This is that guy. So now what is given is just that 1 point, and you have all these things over here that you need to determine. So the picture flips. It's let me draw the same picture as before. These ones here. In this case, we have our upper one, we have our lower one. What is it we know? We will have. So again, let me put the, what was it I put before? These ones here were the ones that I know. But these are the known values. And now the ones that I want to determine, these are these guys. These are the unknown values. Right. The top part here, this is my Tm plus 1. The bottom part here, this is Tm. And so you see, it's more complicated because like before, I would just move from the bottom layer up, but now it's different. Like one point is now going to be dispersed into 3. Right, this one point here is going to get dispersed into 3. Right. That one point is going to lead to 3, right? Because it's n plus 1 and n minus 1. So here we're going to get this is again true for n equal to 1 up to n, and you already know u 0 m, right? That's this guy. This is, and the same thing when you add the upper one, u n plus 1 dr already given. So you don't need to determine the ones out here on the boundary, but you do need to determine all the ones in the middle. And so you're going to get a system of equations here that has to be solved. You have to solve this system here for n equal to 1 up to capital N. So this is a coupled system of equations that you have to solve. And the last one is this Crank-Nicholson. The last one is Crank-Nicholson. Let's briefly mention that. The last one is Crank-Nicholson. This is half of both Euler methods. So you look at the explicit method. That's the one we have here. You're going to do half of that, and you're going to do half of the other one. So you'll say u n m plus 1 is going to be equal to this guy plus 1/2, and then your alpha, and then this stuff. That was what we got from the explicit. Then you go down to the implicit and you take half of that. So you're going to get the other half of, you're going to get a half, so that's the same, and then you get a half of this one plus 1/2 alpha, and then this mess over here, un plus 1. But now we're going to have this m plus 1 up there. And so again, you see that this is going to be implicit. There's going to be another system to solve. If you move stuff around, you will see, what will you see? I will have on the right-hand side 1 plus alpha times un m plus 1. And then I will have other things. I will have minus 1/2. The first guy, and minus 1/2 this last one. So I'll move this to the other side, and then I'm left with what will I have here? I will have 1 minus alpha, and then these two. And this is going to be true for n running from 1 up to n. Okay, so what's on the right-hand side, this is given. What's on the left-hand side, this is to be determined. And so you face, so every time in all of these, you face a linear system of equations, right? And we have to figure out how to solve this linear system of equation in this clever manner, so we can do an implementation that doesn't take forever to do. But these are it's these equations that you'll have to deal with in homework number 5. You have to solve equations of this sort here in that homework. Okay, I think this is a good place to stop. Next time we'll, as I said, the next 2 lectures are going to be shorter, but next time we'll talk more about these methods here, and in particular how to solve this resulting set of linear equations. And you can see that there's something with 3, right? It comes in pairs n plus 1 and n minus 1. So there's something with a triagonal system of equations that's going to come up. So we will spend some time talking about that next time. Are there questions before we finish? Are there questions before we finish? If not, then I'll remind you that there are office hours tonight with the TA, and then tomorrow morning I'll have office hours. And if you have questions, I'll be here from 9 to 10. Alrighty, have a good rest of the day, and I hope to see you tomorrow. Otherwise, I'll see you next week.